before we have a look at the next section, we're just going to remind ourselves of some useful facts that we're going to use. Let's say we've got a complex number, let's call it W, and let's say that it's got an argument of theta. So it doesn't matter whether theta is positive or negative, I'm going to draw it positive just for the sake of making my diagram easy to understand. So it's got an argument of theta there, and let's say that it's got a modulus of r. Then we know that its real part, because of trigonometry, if we draw a right angle triangle like that, the real part of this complex number is going to be its x-coordinate, which you can see from the right angle triangle, if you do some trig, is going to be r cos theta, and the imaginary part is going to be r sine theta. So that gives us two really useful equations which we'll use loads, particularly in the next textbook. So the real part of W is equal to r cos theta, and the imaginary part of a complex number is equal to its modulus times by sine of its argument. I think it's worth at this point trying to relate this to the unit circle which you might have seen before. So if you think about a circle with radius 1, what the definition of sine and cos actually are is if you imagine this green particle moving around the circle and it makes an angle, which I've shown here. So this has an angle of 0.63 radians when the point is there. Then you might already have seen before that actually the definition of sine and cos is, if we think about their coordinates of this green point, the x-coordinate would be cos theta and the y-coordinate would be sine theta. And we could spin all the way around the circle if we wanted to. And you can see that the x-coordinate is going to be cos theta and the y-coordinate is sine theta. Now, this also works if we go in the negative direction. So you know that a negative angle now means that you go clockwise, measured from the positive x-axis. So if we go in the negative direction, the x-coordinate is still cos theta and the y-coordinate is still sine theta. So all we're saying really is we're relating this to complex numbers. If we've got a complex number with modulus 1, all we're saying is that the real part is going to be 1 multiplied by cos theta, and the imaginary part is going to be 1 multiplied by sine theta. And that's true even if theta is negative. It works for all values of theta. So here you can see that we've got minus 0.63 radians, and the x-coordinate is going to be cos minus 0.63, and the y-coordinate, the imaginary part, is going to be sine of minus 0.63, which is negative. And then what we're doing with complex numbers is we're saying, well, we don't always have a unit circle. Sometimes the radius of the circle might be bigger or smaller. So we can change the modulus of the complex number to reflect that change. Let's say we had a complex number with modulus 3. So now we're thinking about a circle with radius 3. And as we move around the argument, it's still the real part, the x-coordinate, and the imaginary part, the y-coordinate, is still related to sine and cos. This time, because the hypotenuse of the right angle triangle is 3, the real part would be 3 times cos of the argument, and the imaginary part would be 3 times sine of the argument. So that's where we get the formulas, r cos theta for the real part and r sine theta for the imaginary part. The reason why we're doing this now is because we need to be really comfortable using the third equation, which is what we get if we divide these two equations. If we do equation 2 divided by equation 1, on the right hand side we will have tan theta. If we do r sine theta divided by r cos theta, we'll get tan theta on the right hand side. And on the left hand side, we'll have the imaginary part of W divided by the real part of W. So this tells you if you do tan of a complex number's argument, then you get the imaginary part divided by the real part. So for example, if we were told that the argument of the complex number 1 minus root 3i, in fact let's make it plus, 1 plus root 3i is pi over 3, then we could use that third equation to write another equation. We could say that tan of the complex number's argument, so tan of pi over 3, is equal to the imaginary part, which is root 3, divided by the real part, which is 1. And the reason why this is useful for this part is we're going to have a situation where we've got a complex number with algebra in it, with unknowns in it. For example, we might have the argument of x plus 3 plus we might have 4i, and we might know that the argument of that complex number is minus pi over 6. Then we can write an equation involving x, because we know if we do tan of this complex number's argument, so this is our complex number w that we're talking about now, and we're told this equation basically says that the argument of that yellow complex number is minus pi over 6. So if we do tan of that argument, minus pi over 6, you're going to get the imaginary part of the complex number. The imaginary part of that yellow complex number is 4, divided by the real part, which is x plus 3. So as we move forward, bear this equation in mind because it's very useful.